So we've learned about the concept of entropy, a measure of disorder, dispersal of a system. And we've learned how to determine whether or not a reaction is spontaneous by looking at the change in entropy for a chemical reaction or process. And we did that by considering the change in entropy of the universe, which we know is going to be composed of the system and the surroundings. And we know that if the sum of the change in entropy of the system and surroundings, otherwise known as the change in entropy of the universe, if that is greater than 0, we have a spontaneous process. Okay? Spontaneous process when delta S of the universe is greater than 0. Now, the tricky thing about this is in order to figure out the change in entropy of the universe, we have to know both the change in entropy of the system and the change in entropy of the surroundings. But more often than not, we're only measuring and concerned with the change in entropy of the system. We only are really worried about the system, about what reaction is going on in the beaker, what reaction is going on in the Erlenmeyer flask, etc. So, is there a way that we can determine if a reaction is spontaneous by using this value alone? And in fact, there is. We can derive another thermodynamic process to do so. And that, not by process, another thermodynamic value or quantity. And that thermodynamic value or quantity is G. Which is the Gibbs free energy. So Gibbs free energy, which we abbreviate with a capital G, since it's a capital letter, we know it's a state function, so it depends only on the initial and final states. Gibbs free energy, by definition, is the energy available to do work. Okay? Energy available to do work. And based on the Gibbs free energy alone, since it is essentially just a measure of the change in entropy of the system, that can tell us, based on measurements of the system only, if the process is going to be spontaneous. Okay. And the way we determine that is by using a relationship that, if we take this and we do some mathematical manipulations, we can figure out an equation which we don't have to understand the process of. But the change in Gibbs free energy, the change in free energy of a system is going to be equal to the change in enthalpy minus temperature times change in entropy. Where this is measured in Kelvin, of course, and the relationship between these three variables allows us to predict spontaneity of a process. Okay? And we can summarize that relatively simply. Okay. If the change in entropy of a system, change in Gibbs free energy is less than 0, okay, then the reaction is spontaneous in the forward direction. If change in Gibbs free energy is greater than 0, positive, okay, it's non-spontaneous in the forward direction. Or another way of saying that is that it's spontaneous in the reverse direction. And last but not least, if the change in Gibbs free energy is 0, the reaction is at equilibrium. So, in class we'll deal with actual quantitative measurements and predicting spontaneity based on calculating Gibbs free energy changes. But what we need to walk away with today is a definition of Gibbs free energy, the equation that relates energy, enthalpy, and entropy, and then these three relationships here that allow us to predict spontaneity based on the calculation of delta G.